Good morning. We are starting to work out a few problems, numerical examples in braking operation of induction motor. So let me start with regenerative braking operation. And the problem statement goes somewhat as follows. It's a three-phase 440 volts, 50 hertz, 6-pole Y-connected induction motor. It has R1 equal to 0.5 ohm, R2 dash, that is the rotor resistance referred to the stator side, that is 0.6 ohms. X1 and X2 are 2 ohms each. And it is a wound rotor induction motor. So NS, that is number of turns in the stator to number of turns in the rotor, the turns ratio is 2. And it is going through regenerative operation. So the machine is going through regenerative braking. So under this condition, what is being asked is, what is the maximum overhauling torque the machine can hold, and what is the range of speed under which it can go through the regenerative braking operation. So this is the first subdivision that is being asked. The second subdivision that is being asked is calculate the speed at which it can hold a load torque of 160 Newton meter. Speed at which the machine can hold a load torque of 160 Newton meter. So this is what is being asked. So first of all, we should remember what is the kind of expression we had derived earlier in the lecture classes for induction motor operation. So if you may recall the induction motor characteristics, it is somewhat like this. We are going to have this as the characteristics of the induction motor. So this region is plugging region. This is the motoring region, whereas this is going to be the regeneration or generating region. So these are the three regions of operation, and this is the speed axis. So this is omega R or omega M, mechanical speed, and this is going to be the torque axis. So when the speed is exceeding the synchronous speed, if I may call this as the synchronous speed, and this is the zero speed and the zero torque, this is the origin of the speed torque plane. So this, whenever the speed is exceeding omega s, that is when we are looking at regenerative operation. So this is going to be the regenerative operation. Okay. So the maximum overhauling torque, if we are looking at, it is same as whatever is the breakdown torque we calculated. So let me write the approximate expression for breakdown torque. The breakdown torque, we wrote this as 3V1 square divided by 2 omega s multiplied by x1 plus x2 dash. This is the approximate expression. If we want the exact expression, we should write this as 3V1 square divided by 2 omega s R1 plus R minus R1 square plus X1 plus X2 dash the whole square square root. This is what we normally write as the exact expression for the breakdown torque or the maximum torque. The first thing that is being asked is for the overhauling torque during regenerative braking. Then we should use the same expression, and the voltage is given to be 440 volts. So let me write this as 3 multiplied by per phase voltage is 440 divided by root 3 divided by 2 omega s. 2 omega s, it is a 6-pole induction motor. So synchronous speed will be 1000 RPM or 2 pi multiplied by 1000 divided by 60, which will be 104.72 radians per second. So we have to use radians per second here. So 2 multiplied by 104.72 and x1 plus x2 dash is 1 plus 1, which is 2 ohms. So this is going to be the complete expression, approximate expression for the breakdown torque. If you want the exact value, then you have to substitute here this value. So this is going to be equal to this root 3 square and 3 will get cancelled. So I can write this as 440 square divided by 4 multiplied by 104.72. So if you want the exact value, you should use this expression. This is approximate value, and this comes out to be 462 Newton meter. So if we are looking at this approximate expression, it will be the same for both regenerative braking operation as well as motoring operation. The breakdown torque will be one and the same. But if we are looking at the actual or accurate expression, they will be different. And for regenerative braking operation, it will be slightly higher. That is the way it is going to be. Okay. This plus or minus sign, what we have, plus sign is generally used for motoring operation and minus sign is used for regenerative braking operation. Okay. Now, what is the range of speed? It is being asked, what is the range of speed during which the regenerative braking operation can take place successfully? So that range is given by from synchronous speed until this particular speed. This particular speed will correspond to 1 plus S max T multiplied by omega S. So S max T we can calculate. So we can write S max T expression again what we wrote in one of the lecture classes. It is R2 dash divided by R1 square plus X1 plus X2 dash the whole square root. So this comes in the denominator. So this comes out to be 0.6 divided by 0.5 square because R1 is 0.5. So that is going to be 0.25 plus X1 plus X2 dash happens to be 2, right? Because X1 and X2 both are given to be, each of them is 2 ohms. So that means even here I have made a calculation mistake. This will be 2 plus 2. So this will be 4. So this will be 4 multiplied by 2, 8. So correspondingly, we'll have to recalculate this torque. So this will be 462 divided by 2. So this is going to be 231 Newton meter. So this will be 231 Newton meter. So here I should write this to be 2 plus 2 the whole square, which is actually 4 square, so that will be 16. So this is going to be 16. So this will be 0.6 divided by 16.25. Okay, so I should write that the range of speed in this particular case will be from synchronous speed, which is 1000 RPM, to 1 plus S max T multiplied by 1000 RPM. So this is going to be the range of speed under which regenerative braking will take place successfully. Now, the second subdivision, what is being asked is the speed at which the machine can hold a load torque of 160 Newton meter. So the load torque is 160 Newton meter. And because it's an overhauling torque and it is a regenerative braking operation, it will be actually minus 160 RPM. Okay. So under this condition, we have to write the expression as the torque, electromagnetic torque, what we develop, that has to be minus 160 Newton meter. This will be equal to 3V1 square divided by R1 plus R2 dash divided by S, the whole square, plus X1 plus X2 dash, the whole square, and in the numerator it will be R2 dash divided by S omega S. Now, please note, because it is regenerative braking operation, slip will be negative. The slip will be negative. In regenerative braking operation, we are going to have omega S less than omega R. So the slip is going to be negative. So in this particular case, we have to write minus 160 Newton meter is equal to 3 multiplied by 440 divided by root 3 whole square. R2 dash is 0.6 divided by minus S omega S. Omega S is 104.72 radians per second divided by, now we should write again R1. R1 happens to be 0.5 ohms. So I can write this as 0.5 ohm plus R2 dash by S, but S is negative. So we should write it as though this is minus R2 dash is 0.6 divided by S, the whole square, plus 2 plus 2. So that is 4 square, which is 16. So we are writing this as the expression corresponding to 160 Newton meter load torque. So here we should be able to cancel this root 3 square and 3. So we can write this as 440 square multiplied by 0.6 divided by 104.72 times S. The whole thing should have a minus sign here. This has to be multiplied by 0.5 minus 0.6 divided by S, the whole square, plus 16. Now, if we solve for this particular equation, we will in all probability get a quadratic equation in slip, from which we should be able to solve for slip. So we will get a quadratic equation in S. So in fact, we can remove this negative sign. If I make this as positive, I can make this also as positive. So we should be able to definitely get an equation, a quadratic equation in S, and S can be solved for, and the negative value has to be taken, from which the speed can be calculated. So we are going to get 1 plus S multiplied by omega S. This is going to be the speed at which this 160 Newton meter torque can be held by the machine. So that essentially solves this particular numerical example. Let us try to do one more problem. This will be a numerical example on plugging. So this is going to be a numerical example on plugging operation of induction motor. So the same motor, the above mentioned motor, that is a 3-phase 440 volts, 50 hertz, 6-pole induction motor is braked by plugging. Is braked by plugging operation. So again, R1 is 0.5 ohms, R2 dash is 0.6 ohms, X1 equal to X2 dash is actually 2 ohms. Okay, so let me write here X1 equal to X2 dash equal to 1 ohm. Doesn't matter because the calculations that I have done are taking into account this resistance as 1 ohm. Calculate the maximum braking current and initial and final braking torques when no braking resistance is used. So the first division is calculate the maximum braking current and the initial and final braking torque when no external resistance is used. So this is the first subdivision that is being asked. Let's try to first of all solve this. So first thing we need to do is to understand the torque speed characteristics during plugging. So if I say that this is going to be the normal characteristics of the induction motor during motoring operation, and let us say this is the speed axis, and this is going to be the torque axis, and this is the synchronous speed, and this is the origin. So this is with ABC phase sequence. If I try to draw the characteristics corresponding to ACB phase sequence, it should actually go on somewhat like this. This is the way it will be. So this again has to be drawn smoothly. So let me draw this as though this is the way the characteristics are. Okay, so this is with A, C, B sequence. Now, if the original operating point had been somewhere here, this is what is the original operating point. So if this is the original operating point, so from here, when you try to look at what is the kind of braking torque that is developed, it's really, really small. This is going to be the braking torque, nothing more than that. But if you look at the current at synchronous speed will be corresponding to magnetizing current, and from there it will keep on increasing. So the current will increase directly somewhat like this. This is the way it is going to increase. So this is the variation of the stator current with respect to speed. If I try to look at it at synchronous speed, it is going to be minimum. It will be equal to magnetizing current, and as the speed increases, decreases towards zero, it is increasing. And this is the starting current, which will be 6 times the rated current. And in plugging operation, it will increase further and further. So it is not going to decrease any further. It will increase monotonously. So if we are looking at no load condition. So calculate the maximum braking current and initial and final braking torque when no external resistance is used and motor was running at no load speed. So no load condition means we are going to assume that the speed is synchronous speed. So first of all, we will say no load condition, the speed is going to be synchronous speed. Speed is going to be 1000 rpm and slip is going to be 0. So plugging slip, if I try to change the phase sequence from ABC to ACB, that is going to be 2 minus S. So this is going to be 2 itself. The slip is going to be 200% or 2. So in which case, we can calculate what is actually the current under that condition. So we can calculate the stator current as V1, which is per phase voltage, divided by R1 plus R2 dash divided by S whole square plus X1 plus X2 dash the whole square root of this. This is what is the stator current, which is going to be maximum, which occurs when the plugging starts. That is, the slip is going to be 2. So under that condition, I can write this as 440 divided by root 3. This whole thing divided by R1 is 0.5 and R2 is 0.6 and slip is 2. So I should be able to write this as 0.6 divided by 2, this whole square plus this is uh, uh, 2, 1 plus 1, 2. So 2 square, which is 4. Now we have to take the square root of this. This is what is going to give us the current. So let me write this like this. This is 440 divided by root 3. This whole thing divided by 0.5 plus 0.3, 0.8 square, which is 0.64, and 2 square is 4. So 4.64 square root of this will be in the denominator. So this comes out to be 117.936 ampere. Okay. So this happens to be the plugging current. This happens to be the plugging current, especially when we are having 2 as the slip or the initial condition when the motor is transitioning from no load condition to the plugging condition. And if we calculate the braking torque at this point, so braking torque at this point. So the braking torque at this point is going to be, the current is already given. So I have to just write 3I2 square R2 or I2 dash square R2 dash divided by S omega S. So 3I2 dash square is 117.936 square multiplied by R2 dash, which is 0.6, divided by slip, which is 2, and omega S. Please remember, this is in the reverse direction because it is ACB phase sequence. So this will be minus 104.76. So 72. So this is going to be equal to minus 119.54 Newton meter. So this is going to be the braking torque when the plugging operation just begins under no load condition. Please note that the current is very, very high, but the torque is not so high because the slip is 2. So that is taking a toll on the torque that can be developed. Okay. Now, when the plugging operation slowly goes towards from here, from this point, it is moving this way and it is reaching zero speed condition. So when it is zero speed condition, if I try to calculate what's the braking torque, so at zero speed, we can say braking torque will be calculated again as 3I2 dash square at zero speed condition R2 dash divided by S omega S, where S is going to be 1. At zero speed, the slip is 1. So we should be able to calculate what is I2 dash at zero speed condition. So that is going to be, we can calculate this value as 440 divided by root 3 divided by R1 plus R2 dash, which is 0.5 plus 0.6 divided by S means S is 1. So I can simply write 0.5 plus 0.6 whole square plus 1 plus 1 whole square root of this. So that gives what is the I2 value, and that comes out to be 111.3 ampere. So I2 dash is 111.3 ampere, and the torque what we get under this condition, if I use this expression, I should write 3 multiplied by 111.3 whole square multiplied by 0.6 divided by slip is 1 and synchronous speed is 104.72. So this will give us what is the kind of torque is being developed, that is 70.97 Newton meter. So again, I can use a negative sign if I try to look at this from the point of view of the original motoring operation. Please verify all the calculations, but please note that here for 117 amperes, we got 119.54, whereas here we are getting for 111.3, 70.97. There's something not very correct from the point of view of calculation, because you can see that under plugging condition, we should have very, very small torque to begin with, and it should have increased quite a bit after it has reached the zero speed condition. So please check the calculation thoroughly, because this torque should have been higher than what we got in the previous case. So maybe there is something the matter with the way the calculation has been done. So you please check the calculation for sure. Okay. One more problem on plugging. So let me try to do one more problem on plugging. This is another numerical example on plugging. This example, the problem statement goes as follows. It is a 440 volts, 50 hertz, 6 pole, Y connected induction motor. It has R1 is equal to 0.08 ohm. R2 dash is 0.12 ohm. X1 is 0.25 and X2 dash is 0.35 and XM is 10 ohms. That is the magnetizing reactance. Now the question that is being asked is, what should be the external resistance to be connected in the rotor circuit so that maximum torque is obtained at the beginning of plugging operation when originally the motor was running at no load. When originally the motor was operating at no load. So let's try to solve this. See, if we look at it from the characteristics viewpoint, if let us say this is the speed torque characteristics of the induction motor, and if I am going to initiate plugging operation, the plugging operation should work with ACB phase sequence. So I should have it somewhat like this. This is what is the plugging operation with ACB phase sequence. So this is ABC, whereas this is ACB, and this is torque, whereas this is speed. And original operating point was probably somewhere here. And we are looking at plugging being initiated from this point. So we are changing the stator supply from ABC to ACB. So the braking torque, what we get is really, really small. So if I want to increase the braking torque and I want to make that equal to the breakdown torque, then I should be inserting a large rotor resistance such that the stable operating condition extends until here. So this is with increased R2. When I increase R2, I'm going to have a huge amount of droop in the characteristics, due to which we are going to have the induction motor characteristic shifted somewhat like this. So this is the way when R2 is increased. So this is with R2 increasing. When R2 is increased, the droop is going to increase further and further, and we are looking at this with ACB phase sequence. Okay, so I have to write the expression for S max T, and S max T in this particular case has to be close to 2. This has to be, S max T has to be equal to 2. So this should be equal to R2 dash plus R2 external, whatever is the external resistance that I want to include, divided by R1 square plus X1 plus X2 dash the whole square root. So this has to be our S max T. So this will be equal to, I can write R2 dash plus R external will be equal to 2 times R1 square, which is 0.08 square, and X1 plus X2 dash the whole square. X1 is 0.25 and X2 dash is 0.35. So that is 0.6, the summation of these two. So I should say 0.6 square. And I have to take the square root of this. So this comes out to be 1.2106. So if I want what is the R external value, R external dash should be 1.2106 minus R2 dash. And R2 dash value is 0.12. So our external value comes out to be 1.0906 ohm. So this is the external resistance. If it is asked, calculate corresponding Tmax value. In case the corresponding maximum torque value, if it is being asked, we can either use the breakdown torque expression, which is approximate expression 3V1 square divided by 2 omega s multiplied by x1 plus x2 dash, or you can use the detailed expression what we wrote. This comes out to be about 1540 Newton meter. So this is the breakdown torque what we have got in this particular case. Okay. Now let me do one problem on DC dynamic braking. So we are going to do one numerical example on DC dynamic braking. So the problem statement is somewhat like this. The magnetization characteristics of a 5 kilowatt 50 hertz 4-pole Y connected induction motor when a connection as shown in the figure is used is as follows. Magnetizing current in ampere and induced EMF in volts. So this is 0.898 ampere, 74 volts. This is 2.86 amperes. It is 199 volts. And 8.2 ampere, that is 201 volt. volts. So this is the magnetization characteristics that is given. The connection diagram I need to draw. So the connection diagram is somewhat like this. One phase is here. The other two phases are connected together like this. And then the magnetizing current is passed through the induction motor and the voltage is measured here. So this is the voltage. So regeneration characteristics generally is magnetization characteristics is generally obtained by running the machine at a particular speed or rated speed and pushing a magnetizing current through the windings. the windings are connected like this. Let me call probably this as A phase, this as B phase, and this as C phase. So this is how it is connected. And the magnetizing current is given by IM, what is flown through this and passed through this, and what is the kind of voltage that is getting induced when it is driven at a particular speed. Now, what is being asked? What is being asked is calculate the torque corresponding to DC dynamic braking with the stator winding connections as shown above when a DC current of 12 ampere is passed. Calculate the speed and rotor current corresponding to IM equal to 8.2 ampere. So what is being asked is corresponding to the last particular operating point. So before we proceed, we need to look at, first of all, for this kind of connection, how are we going to calculate the equivalent AC? So first of all, let us try to calculate the equivalent AC current. You may recall that in the lecture class, we had talked about two lead connection. So there are two different types of connections where only two leads of the induction motor are used. So in two lead connection, what we looked at was something like this. If we call this as A phase, these two are B phase and C phase respectively. A phase is going to be left completely free. It's not going to be connected anywhere. Whereas for B phase and C phase, we are going to connect a DC supply somewhat like this. So this is going to carry a current of, let us say, ID like this, whereas this is going to carry the return current of ID. So if we are looking at this as B phase and this as C phase, so if the resultant we need to look at, we are going to have, let us say, B phase MMF is like this and C phase MMF is normally like this. But because it is carrying a return current like this, we have to invert it and show it in this direction. So let us again draw it properly with 120-degree disposition. So this is A phase and this is going to be B phase and this is going to be C phase. So A phase is 0, FA is 0 for now, and FB is N times IDC if I'm talking about the number of turns in each of these phases as N. And this FC is going to be minus N times IDC because the current is a return current. So rather than drawing it like this, I have to draw it in the other direction to show this as N times IDC when it is in the reverse sense, when it is indicated in the reverse sense. So this is going to be FC actually. So because of which, when I add these two together, I'm going to get it somewhat like this. So this is the resultant. So this is going to be, this is 30 and this is also 30 degrees. So this is cos 30 multiplied by 2 times NIDC. So this is actually NIDC cos 30 plus NIDC cos 30. So that is going to be 2 times NIDC root 3 divided by 2. That's why we get this as root 3 times N times IDC. So this is the resultant, what we get for two-lead connection when we talk about two-lead connection. And if I want to calculate the equivalent AC current, in the lecture class itself, we said that if I'm going to have a per phase current of IS RMS value, multiplied by root 2, which is the peak value, 3 by 2 times that multiplied with the number of turns per phase. So this is going to be the peak value of the resultant MMF or revolving magnetic field. So if I want an MMF which is having a strength of root 3 times NIDC, I should be actually pumping in a per phase current of IS in every phase so that it ultimately results in a similar strength MMF or magnetic field. So from here, I should be able to calculate the AC equivalent current, which is per phase RMS current. That will be essentially IS, which is equal to, now I should be able to cross this and write this down as root 2. And similarly, this and this, I should be able to cancel this out as root 3. So this will be root of 2 by 3 multiplied by IDC. So this is the equivalent current, equivalent RMS AC side current, which can be calculated from the DC current by looking at the resultant MMF. The same way, let us try to look at the three-lead connection, what is shown already in the figure. So in the three-lead connection, what is shown in the figure, let me show the figure once again. So this is the three-lead connection that we are going to use. So in the three-lead connection, we are having on one side, I'm going to have A phase, which is carrying the current, which is like this, which is ID, and it is going to pass through B and C phases. It is going to divide itself into two halves. So this is going to be ID by 2. This also is going to be ID by 2. Only thing you have to realize is in A phase, the current is flowing into the phase, whereas B phase and C phase, it is flowing out of that particular phase. And then I'm going to connect these two together. And finally, this terminal is going to be connected to the DC source, somewhat like this. So this is the DC source. Okay. Now, first of all, the resultant of B and C phases. Let us try to calculate. So if you look at it, I'm going to have B phase MMF somewhat like this, and C phase MMF is like this. This is 120 degrees. So when we apply the law of parallelogram, so this is going to be NID divided by 2. This will also be NID divided by 2. If I assume it is minus ID, it is minus ID both ways. So I don't have to worry about the sign too much. And I'm going to have the MMF like this now. This is the resultant. So resultant is somewhat like this. This is resultant. So F resultant will be NID divided by 2 cos of 60 plus NID divided by 2 cos of 60. And cos 60 is half. So we will have NID by 2 as the resultant. So this is going to be, the resultant is going to be NID divided by 2. And this is the resultant that has to be added to FA. So FA is NID, which is in, let us say, this direction. This is NID. And we are going to have NID by 2, which is in this direction. But this is minus NID by 2 because the current is flowing out of B and C phases, whereas current is flowing into A phase. So I should add this also in this direction, which will be actually plus NID by 2. This will be the resultant of B and C phases. So when I add FA plus F resultant of B and C, I am going to get 3 by 2 times NIDC. So this is going to be the resultant when I have a 3-lead connection as shown in the figure. So I should be able to say 3 by 2 times IS RMS value, which is multiplied by root 2 to get the peak, multiplied by the number of turns per phase, that should be equal to the resultant MMF, what I have got here. So what we are looking at is what kind of AC current, per phase AC current on the 3-phase side. If it is a balanced 3-phase supply, that will develop the same strength MMF as that of the 3-lead connection in the case of DC dynamic braking. So now we should be able to cancel this 3 by 2 with this 3 by 2, and this N is cancelled out with this N. So I should say if the per phase RMS current in the case of a 3-phase balanced supply is IDC divided by 2 root 2, then in that case, we are going to develop the same strength magnetic field as that of the DC dynamic braking in 3-lead connection. So the 3-lead connection actually gives a current equivalent of IS equal to IDC divided by root 2. So coming back to the problem basically tells that 12 ampere of current is being injected during DC dynamic braking. So first of all, let us try to work out the equivalent AC current. So let me just say equivalent AC current per phase should be 12 divided by root 2. That is what is the overall current. So that is something like 8.485 ampere or something like that. So this is going to be the AC RMS current per phase. So we are actually continuing with the DC dynamic braking problem. And we are looking at what is the kind of rotor current and the speed and torque we are going to get. So if you may recall, we drew the DC dynamic braking current, DC dynamic braking equivalent circuit for an induction motor somewhat like this. If I am injecting a current of IS, which is equivalent to synchronous frequency, and let us say this is R1, this is going to be X1, and this is XM. And we are going to have the resistance to be R2 dash by capital S, where capital S is equal to 1 minus small s, where S was the original slip. That's what we defined, because we said that the DC field is a stationary field, whereas rotor is rotating at the speed of omega r. So rotor is rotating at a speed of omega r, which is actually equal to 1 minus s times omega s. But currently, we are going to see that the DC field is stationary. So if the rotor is looking at the DC field, it will look at it as though the DC field itself is rotating in the opposite direction with the speed of omega r. So that is the reason why we have taken that corresponding to the induced frequency and so on. So now to complete the equivalent circuit, I should draw here x2 dash, and this is the overall equivalent circuit of the induction motor on a per phase basis when we are implementing DC dynamic braking. And what is the kind of current we are injecting currently? We are injecting IS equal to 8.485 amperes. So I have to write this as 8.485 ampere. So this is what we are injecting. Now that is going to divide itself into two portions. This is going to be I2 dash and this is going to be IM. And this will follow current division rule. And what is the XM value? XM value we will be able to calculate from what is given in the magnetization characteristics. It is given as 201 and 8.2. The magnetizing current is 8.2 and the induced EMF is 201 volts. So I should be able to write XM equal to 201 divided by 8.2. This is going to give us what is the XM value. And that XM value comes out to be, when you calculate it like this, that is 24.5 ohm. Now, because XM and R2 dash by S plus JX2 dash, both of them are parallel to each other, I should say E square will be equal to IM square XM square, which is also equal to I2 dash square multiplied by R2 dash divided by S the whole square plus X2 dash square. Okay, so this is one thing. So let me write this as equation 1. By current division rule, I should be able to write when I take IS into account, if I want to calculate what is I2 dash, I should be able to write this as I2 dash square will be equal to IS dash square multiplied by whatever is the other impedance, which is XM square divided by the total impedance of the two parallel paths, that is R2 dash by S the whole square plus X2 dash plus XM the whole square. So I can write this in a different format. I can say that IS dash square multiplied by XM square should be equal to I2 dash square multiplied by R2 dash by S the whole square plus X2 dash plus XM the whole square. So let me call this as equation number 2. So comparing equation number 1 and 2, I should be able to write this as IS square minus IM square multiplied by XM square. So I am using these two portions, that is this and this, these two portions, and that should be equal to I2 dash square multiplied by R2 dash by S whole square plus X2 dash plus XM the whole square. So if I compare 1 and 2, this portion will be cancelled out with this portion, and this X2 dash square will be cancelled out with this portion. So I should be able to write this as I2 dash square multiplied by XM square plus 2x2 dash xm. Okay, so this is essentially when I subtract 2 minus 1. This gives this particular expression from which I should be able to write this as I2 dash square should be equal to IS square minus IM square multiplied by XM square. I can bring it down. So this will be 1 plus 2 X2 dash divided by XM. So this equation number 3 will be able to give me the value of I2 dash if I know what is IS, what is IM, and what are all these values. So I should be able to calculate what is I2 dash. And once I have I2 dash, I have rest of the things, I should be able to calculate the slip as well. So I can say basically from equation 3, I2 dash can be deduced. And from equation 1, if I know I2 dash also, I should be able to, let me write this expression clearly. That is E square minus I2 dash square X2 square. So I can say from equation 1, E square equal to I2 dash square multiplied by R2 dash divided by S whole square plus X2 dash square. This is equation number 1. So from which I can say E square minus I2 dash square X2 dash square, right? That will be equal to I2 dash square multiplied by R2 dash divided by S. So from here, we should be able to, if I know everything, I should be able to calculate what is R2 dash by S. So I can say E divided by I2 dash whole square, okay, minus X2 dash square. Square root of this is R2 dash divided by S, from which, so if I call this equation as 4, so from 4, S can be inferred. And hence, the speed and the torque. So let us try to implement this now. Actually, how we are going to do the calculation, let us see. So we said that to calculate S speed, I2 dash and torque. So how are we going to do that? That's what we are going to see. So we said that the stator current AC equivalent current that we calculated as, I think we calculated that as 8 point, let me check, 8.485 amperes. That we calculated as 8.485 amperes. IM is 8.2 and XM is 24.5. That's what we calculated. Okay, so let me write those figures clearly. So that is 8.485, which is IS, and IM is 8.2 ampere, and XM is 24.50. Now, with these values in place, we can first calculate what is the rotor current value. So the rotor current value, we had already written the expression. The rotor current value is given by expression 3. So I2 dash square equal to IS square minus IM square plus 1 plus divided by 1 plus 2x2 dash divided by xm. So we can write IS square minus IM square divided by 1 plus 2x2 dash divided by xm. This is what is I2 dash square. So this we can calculate as 8.485 square minus 8.2 square divided by 1 plus 2x2 dash. So x2 is 4. I think it is given as 4. Let's see. X2 is given as, oh, so here I should have given what is R2 dash and what is X2 dash. So X2 dash is given by 4 ohm, that is the value. And let me check what is R2 is 3 ohms. So these two values, sorry, I had forgotten to give earlier. So this is 4 divided by 24.5. So this is 2 multiplied by 4. Okay. So from here, we should be able to calculate what is I2 dash. And I2 dash comes out to be 1.89 ampere. The next step is to calculate the slip. So to calculate capital S, which is actually 1 minus S. So this capital S, I should be able to calculate as this particular equation number 4, whatever we have written. So E is already given. E is 201 volts and I2 dash is given. So let me write that expression once again. E divided by I2 dash whole square minus X2 square. So I can say E divided by I2 dash E square divided by I2 dash whole square minus X2 dash square root of this will be equal to R2 dash divided by capital S. So in this, we know all the values. We know what is E. We know what is I2 dash. We know what is X2 dash. We know what is R2 dash. So S can be inferred from here as 0.02823. So this is the 1 minus S value. So S times omega S, which is 50 Hertz, or in this particular case, because it is a 1000 RPM machine or 4-pole machine, this is a 4-pole machine, so 1500. So omega S is 1500 RPM. So this comes out to be 42 RPM. So the speed is 42 RPM. And finally, if I want to look at what is the torque is 3 I2 dash square R2 dash divided by S omega S. So that is 3 multiplied by 1.89 whole square multiplied by R2 dash. R2 dash is 3 ohms and divided by S is 0.02823 and the synchronous speed is 157 radians per second. And this comes out to be 7.254 Newton meter. So this gives a very, very meager amount of torque, especially at an RPM of 42 RPM. So when the speed is very, very small, we are going to get a very, very small torque as well. So generally DC dynamic braking again is not effective unless we modify the rotor resistance appropriately. So this is also good for wound rotor induction motor. So we have seen effectively one problem in plugging, one problem in DC dynamic braking, and one more problem in regenerative braking. I would request you to look into some of the books like G.K. Dubey's book or other drives books so that you would get familiarized with many more problems in the braking of three-phase induction motor. Now, basically, there are three topics, rather four topics that are still pending as far as the induction motors before we conclude the three-phase induction motor. The first and foremost thing that we might have to do is CSI, current source inverter fed induction motor drive. This has not been dealt with until now. The second one is if an induction motor is fed with non-sinusoidal supply. So performance of induction motors with non-sinusoidal supply. This is one more topic that we need to deal with. Then we will talk about FOC, field-oriented control of induction motor drives. And we will conclude the topic of induction motor with direct torque control of induction motor drives. So these are the four topics that we will be dealing with one after another in the next